This video is about capillary pressures. There are two opposing pressures that are present within the capillary. One is pushing out and one is pulling in. The outward force is due to the blood pressure. So the heart is generating this pressure. We know it starts out at like 120 millimeters of mercury close to the heart, but then by the time it gets way down here to the capillaries, it's about 35. In terms of the capillary pressure, we call this capillary hydrostatic pressure. So literally the pressure of the fluid of the blood on the walls of the capillary. The second pressure is due to albumin, which we know is made by the liver. This is an inward force, so these two are opposing each other, and we call this the blood colloid osmotic pressure, BCOP. Colloid for the protein, osmotic because this is literally pulling water into the capillary towards it. And so these two pressures are essentially opposing. So in this video, I'm going to talk about the opposing pressures at different points in the capillary, kind of in terms of like tug of war. So the blood pressure is pulling out, capillary hydrostatic pressure, and the albumin, the blood colloid osmotic pressure, is essentially pulling in. And so we begin the capillary. So here's the red side, the arterial side, and we see blood loses oxygen, it becomes purple, and then finally on the venous end, it is blue. And so at the very beginning of the capillary, the blood pressure is as high as it's ever going to be. And so if this was tug of war, essentially the blood pressure, we see here, the blood pressure is actually winning. And so this is essentially the net movement of substances across the capillary wall. Okay, so at the beginning, the blood pressure is pulling, or technically pushing, a lot harder than the albumin, the blood colloid osmotic pressure. However, because of this hydrostatic pressure, a lot of stuff is actually leaving the capillary. Only the really small stuff. So water is leaving, small molecules like glucose, like vitamins, amino acids. These are able to actually pass through channels and out into the tissues. And so that initial blood pressure is actually going to start to go down. So this guy is going to be pulling with less and less force than it started in the beginning here. Right? And again, that's because we are losing water over this membrane. Blood colloid osmotic pressure, remember, this is formed due to albumin. And so albumin is actually too big to fit through channels. So it is going to stay in the capillary bed and actually just drain right into the venous end. And so the blood colloid osmotic pressure due to albumin doesn't really change. Right, so this guy is pulling just as hard as ever, but this one is getting a little bit weaker. And so as we continue down through the capillary, right, at first hydrostatic pressure is winning, but soon the hydrostatic pressure essentially reduces so much that it equals the osmotic pressure of the albumin. And so we can see here they're kind of at a stalemate. We don't really have anything flowing out. We don't have any net movement out or in. It's approximately equal at the middle of the capillary. Okay, the blood pressure is going to reduce so much, right, again, because we're losing all of this water. Okay, blood pressure reduces so much that by the time you get to the venous end of the capillary, the blood colloid osmotic pressure is winning. That is, they're both still active, right? This one has been the same all along, right? The amount of albumin has not changed, but what has changed is essentially the strength of this guy, the strength of the blood pressure. And so by the time you get to the venous end, there is a greater inward pull of water and other stuff than there is an outward flow. And so we get a net reabsorption of stuff from outside the capillary. Okay. The book shows this, so it shows these numbers. At the beginning of the capillary, the capillary hydrostatic pressure, the blood pressure, is about 35 millimeters of mercury. This is greater than the blood colloid osmotic pressure, so the albumin pulling in. And so we get this net outward flow of water, small molecules, etc., into the tissues. Right? Because of this, the capillary hydrostatic pressure, the blood pressure, is going to reduce by the time you get to the middle of the capillary bed, so much so that the blood pressure equals the pressure of the albumin. Okay, so 25 and 25, this is an equal pulling in and pushing out, and so there's no net movement of substances across the membrane. By the time we get to the end of the capillary bed, again, our little albumin friend here is winning. Note that the 25 hasn't changed this whole time. The 25 is the same. So he's pulling just as hard as ever, but what is changed again is this capillary hydrostatic pressure. The blood pressure has dropped down to about 18, and so now the inward pull is greater than the outward, and so you get a net flow of substances back into the capillary. And so what this does is it causes water, small molecules, etc., to flow out at the beginning of the capillary bed and essentially get sucked back in by the time the blood drains out of the capillary bed and back into the venous system. Again, this is a video on capillary pressures, two opposing pressures, the outward blood pressure and the inward osmotic pressure caused by albumin. Thanks.